see for how many people is the first time coming out to the Hadoop meetup event? Okay, so just to give you guys a quick overview, we do about one event a month. It's usually topics related to Hadoop, and we move it around the area. Sometimes we have it in Virginia, sometimes we do it in Maryland. So since we had it in Maryland, the next one will probably be in Virginia, and we do it in DC as well. To go into that a little bit more, if anybody is, or anybody's company interested in hosting the meetup in the future, please come see me sometime during the meetup. Usually one of the ways to become a sponsor is to host an event, provide us a venue, and to have an event. With that, does anybody have any open source news or announcements or meetups that they want to announce?
Thanks. I'm Charlie Greenbacker. I can yell or just use the mic. Charlie Greenbacker. I'm a data scientist at Berryman Technologies, focusing on NLP. Last month I started the DC Natural Language Processing Meetup. We're having our first event on the 23rd of April. It's actually co-listed or cross-listed with Data Science DC. The focus is natural language processing and big data, and I think there's still about 100 spots open, so if you haven't signed up, we'd be glad to have you. So it's meetup.com/DC-NLP or on Twitter @DCNLP. Thanks.
Does anybody else have any announcements?
We're having a Cumulo hackathon. If people are interested in hacking at Cumulo. On May 4th, Booz Allen is hosting a Cumulo hackathon in Northern Virginia. If you guys are interested in contributing to the Cumulo project, please join us. There is information about it on the meetup site for this group, so find out all the information there.
Hive users that want to hack around with Cumulo and tie the two together. As of Hive 10, you can now do that. The code for that I should have posted up soon to the Cumulo group once they approve it. So anybody that wants to play with it, you can now do that. Same way you could with HBase, you can tie the two together seamlessly.
Anybody else? Alright, so last thing, I want to thank all our sponsors. First, OpenSource Connections for sponsoring. You guys want to say anything about your company? A little bit. Okay. Also, Microsoft for providing us this venue. Anybody from Microsoft want to come up and say something?
Welcome everyone. Happy to have you here. We do have an event tomorrow morning at Reston Microsoft Technology Center for anyone interested. It's a half-day event tomorrow morning, the Reston MTC. Anyone is welcome to come, covering the Microsoft Big Data story and also Parallel Data Warehouse.
Finally, I want to thank my employer, Booz Allen, who've been hosting this event since, I think, 2009. Usually do the pizza and soda, and as well as organizing and getting the speakers and the events and the venues and everything together. So, I guess thanks to my employer. With that, I'm going to hand it over to the speakers for today.
So we will be doing Prezi today. I hope you've taken your motion sickness pills. Mirror, yeah. All right, change it. Can everyone hear me okay? Quick mic check. How about you, Doug? Can everyone hear me? Yep. All right, okay. Try not to scream. Just make it full screen. Yeah. All right. All right. So first things first, introductions. Our company is named OpenSource Connections, and we do largely enterprise search applications and big data applications for government and for commercial types. My name is John Berryman, and tonight I'm going to be giving more of a theoretical aspect to our current endeavor, which is imbuing Solr with semantic search and with recommenders.
And I'm Doug Turnbull. I'm going to be playing the role of plumber and bit twiddler in this talk to John's math wizard. So that will be my role.
He's my plumber.
Yes. I was very confused there were no pipes.
All right, so we're going to talk about how we used Mahout to give Solr the ability to do latent semantic indexing, which we'll show in a little bit is basically synonymous to the recommendation problem. We'll talk about some of the problem, the background for the problem itself. Then we'll go into a more mathematical discussion. Once we discuss kind of the math behind our ideas, we'll talk about how we took our approach, and then we'll talk about where our approach took us. And finally, we'll give some of our, we're at the point where we have some preliminary results, nothing big and earth-shattering yet, but we'll give you a demonstration of where we are, and finally kind of wrap up with what our next steps are. So let's take a look at the problem. To understand the need, first you have to understand how a really basic search engine works. And so let's consider a search engine that indexes these three documents. Brown foxes jump, the quick fox runs, and brown dogs are running. All right, so not very interesting document set. But the first thing that a search engine is going to do once it takes these documents is it's going to chop up these documents into tokens and basically create a bag of words type model of each of the documents. So in the case of document 1, we know that it contains brown, fox, jump, and that's it. Document 2 contains fox and run, and it contains quick 2 times. And document 3 contains brown, fox, brown dog, and run. It's not a search engine yet. The thing that we really need to do to make it where it can find documents fast is basically we take this and transpose it down here in the bottom left corner. And what you've got there is called an inverted index, where we've indexed the documents according to the terms that they contain, rather than the vice versa. After you've done this, search is a pretty straightforward procedure, at least in the Boolean case. If I want to search for any document that contains brown and fox, then I go over to my inverted index, I find the corresponding rows, which are basically bit vectors, and we're talking about and, so I and them together, and as you can see, it turns out the document that we need to return is the first one. And so in some sense, search is as simple as that. So what's the problem here? What's missing? The thing that's missing is really what we're doing is just a token match. You can find any document that happens to match the exact token you type in, but a lot of times you want to allow your users to search according to meaning. They've got something in mind. They don't have necessarily the exact token that's in a document. And so to consider this, let's look at another set of documents. Yellow banana peels. A banana is a long yellow fruit. This mystery fruit is long and yellow and has a peel. Question is, what happens if I search for bananas? If I'm doing a normal token matching search engine, then I get the first one back and the second one back, but the third one doesn't have the word banana in it. Now, to a human, I mean, maybe even a human that doesn't know too much about English, by reading these first two documents, you've got enough context already to know that the third one probably belongs back too. We're talking about something that's very closely related to that. And so that's the pain point that latent semantic indexing resolves, that semantic search resolves. So some of you are probably here tonight to hear about recommenders, and you think, well, when do we get to that? As it turns out, we can talk about a term document matrix, as we have been, or we can talk about a user item matrix. And fundamentally, the problem is the same thing. Just like not all terms occur in every document that are talking about those terms, similarly, not all people have watched movies in particular genres, but it'd be good to understand kind of the concept of a genre. So they're fundamentally related and maybe even at times synonymous. So we're starting to get an idea of our goal. We're starting to understand an approach that we want to take. Somehow we want to be able to pull the terms out of the Solr index, and we want to kind of blur their meaning together so that if we don't have a document about banana, but it has yellow and fruit and long and peel, then we start to get some of that feeling out of it. And once we got that essence extracted out of these terms and kind of smeared around a little bit, we want to be able to push it back into Solr so that it's searchable. Now, I'm intentionally using very vague terminology because right now I haven't really built up how that works. So it's a lot of magic right now. This is what we want to do. But in order to understand what that must really mean, let's take a step back and look at the math events. So what does it really mean to blur meaning? A good example is just take the case of, we'll go back to the recommender problem right now. Take the case of this very small movie user matrix. It's probably a bit small for most of you, but I think a lot of the things that we'll be drawing don't really emphasize the actual specific numbers. Let's consider this matrix of users' ratings of various movies. Fundamentally, what this little matrix is, it's a mapping between these two sets. If you want to understand how a movie is related to a particular user, you go to their column and get an understanding about their tastes. But users haven't watched all the movies. So we run up against the same fundamental problem as I showed you a couple slides back. A good tool that we have in math to start to pick apart the idea of meaning is the singular value decomposition. And what that does is it takes this one matrix and it breaks it up into 3 matrices. So that if I took these matrices and multiplied them all back together, we would get back to the original matrix there on the left. Now you might be thinking to yourself, isn't this just more complicated? We started with something that was 3 by 5 and now we've got 3 matrices that are just about as big as that over there, and the numbers are all floating point now all of a sudden. But the way that we can use this is by applying meaning to each of these individual matrices. So, whereas on the left side I was comparing movies to users, on the right side I've kind of introduced a middle ground. I'm not interested on exactly how a movie was viewed by a particular user, but I'm interested first in how a movie is weighted into a particular genre. Certain movies fit in certain genres, horror, action, comedy. So that's what the first matrix is. It's a relationship between those two groups. The second matrix is talking about the strength of each of these genres. And you might not be able to see this terribly well, but everything is 0 in this matrix except for the diagonal. And the diagonal is highest numbers at the top left, and they get lower and lower until it's very low influence at all. But each one of these numbers represents how strong a particular genre is in our data set. And finally, we've got a matrix that relates the genre and how interested a user is in a particular genre. So a lot of times, matrices get all confusing. It's a lot of stuff to absorb at once. So one thing that helps me to do is to step back and think about how this applies to a single cell in the original matrix. Now this matrix is movies to users, so what if this row is for the movie Child's Play, Chucky, and this column reflects my views of the movies. So what this cell literally says is that my value of the movie Chucky is equal to 2. Now if we apply that math that we saw in matrices, if we actually write out an equation for what happens to this specific cell, then we're looking at three different entities added up, entities multiplied together and added for every genre. We're looking at what is the value of Chucky for the genre that we're interested in, and we'll go through all the genres. What is the strength of that genre in our data set, and what is my valuation of that genre? How much do I like it? And it's still a little fuzzy until you get to an example. Let's consider the genre of action. Chucky has some action, so it's got a little bit of value there. Action is one of the most popular genres in our data set, so it's 5.3. And I basically like action movies. So if you multiply all these things out, then action's contribution to my like of this movie is 0.5. Romance. Romance is the second highest genre. Chucky, not much romance involved in Chucky. Now for our horror fan lovers, Chucky 2 is Chucky's Bride. There's a little bit of romance there, but this is Chucky 1. And I'm a sucker for romance. Not as great as action, but I like it all right. So, but multiply all those terms together, and my value still ends up to be 0 for this particular genre in Chucky. Horror is kind of the opposite picture. I like horror movies. They're kind of cheesy horror flicks, fun every once in a while. Horror is a bit further down in our movies. Most of them are about action or romance. And Chucky has a high ranking in horror, so you add them all up, you get to 1.4. And as you keep going, the strength of the genre becomes less and less and less and less, until we get to very, very specific niche genres. Scary doll movie is my example in this bottom row here. And even though Chucky is a perfect example of a scary doll movie, in our data set, we just don't care. And, I'm not a big fan of scary doll movies. So if you add them all up, the contribution of that, even though it's such a strong, Chucky has such a strong relation, it's still very small. So it begs the question, do we even need that bottom row? Do we need the bottom rows? Maybe we could throw that away and get the big picture just looking at this top set. And that's exactly what we have to do to blur the meaning. If we were to take the less strong genres and just chop them out completely, then effectively we have zeros in both of those rows. We don't have to do as much multiplication. We start cutting off rows and columns of the original matrices on both sides. And when we multiply these new kind of truncated matrices together, we get a matrix that is very close to the original, but not quite the same. And the differences here are informative, because this matrix was made with a broader brush. You just get a basic understanding of the genres and the communities that watch particular movies and the types of movies in these genres. And when you ignore the noise at the bottom, you start to notice things like in this example, our user has not seen, our user 1 has not seen movie number 2, but in this approximation of the matrix, basically what it's telling us is that they probably like it. They probably give it a 3.8 rating. So you can use this directly to start making recommendations to your users.
How do you know the 5.4 is action movie or 4.3 is a romance? You have to manually.
When you do a late, so the question was, how do you know these numbers?
This number means an action genre or romance genre.
So, okay, that's actually a good question. How do you know that this is an example, but how do you know that this refers to an action genre? How does this comedy? And that's a good point. When I say genre, I should actually qualify it a little bit. This is, they tend to bunch together, and we've got an interesting example later from our data set around genres, but they don't tell you, hey, I'm action. You just, if you look at all the terms, you'll see Star Trek and Indiana Jones and all this stuff bunched together. Yeah, so it's kind of a computer's opinion of what things typically covary. It's really a measure of how well films covary. It's a statistical concept. Yeah.
So it's
It's,
but computer somehow think this how you want to.
let me get to the next slide, because I might be, I better keep going before we get to the next part, actually.
Sure, sorry.
So it turns out that this blurring of meaning is called rank reduction. And for those of you, and this might speak to some of your questions, for those of you who like kind of a visual interpretation of stuff, what we can, the visual way of interpreting latent semantic of singular value decomposition is you can take each row in that matrix and consider it a point in high dimensional space. In this case, we've just got 2 users, so we can still visualize it. And what latent semantic analysis does is it pretends that these things fall in a normal distribution, basically an ellipsoid type distribution. And what those values along the matrices are is actually the measure of how long this ellipsoid is. So it's the direction of most commonly covariating terms, ideas, movies, users, etc. What latent semantic, what rank reduction does though, is it says, okay, we got this high dimensional pancake, let's look at the dimension in which it's already skinniest, and let's go and just flatten it all the way out. And let's pretend all those original points actually lie in this plane. So it's a way of talking about the same information, but in much less dimensions. And there's a lot of analogy that I'd love to go into, but probably won't have time quite yet. So there's several different approaches to rank reduction. Singular value decomposition is just one of them, and it happens to be a good one for kind of wrapping your mind around the subject. Alternating least squares is really interesting. It kind of gets around some of the heavy lifting of SVD, and this is actually the technique that was used to win the Netflix challenge. And stochastic SVD is yet another one, and it's the one that you'll see in a moment that we went with. So at this point, our goal is a little bit more clear. We've removed some of the magic that we talked about in the first set. Rather than just pulling the terms out, we know that we're going for the term document matrix. And rather than just blurring meaning, we now understand that we are going to rank reduce this matrix. And at that point, we can shove the new fuzzy term vectors back into Solr and make it searchable in just the same way that Solr deals with a normal document. All right, so now Doug's going to talk about our approach, and then we might have a little time for questions before we go on our first break.
Hey guys, how's it going? So this is kind of when John and I were talking about how we were going to do this, and Googling around for what Mahout could do, and the dude was able to give us. This was basically where we started. In short, we need to pass things through Mahout, do some magic machine learning on them, and bring them back into Solr. Mahout has a capability of extracting term vectors from Lucene. Solr is built on top of Lucene. And this capability exists, so we thought, great, we have, after our Google searches, we were first finding this out, we said, great, we'll be able to pull term vectors into a format that Hadoop can understand. Finally, we found a couple ways to do SVD. We started with, we just found Mahout SVD, which is a command line that you can run. So that made us even more excited. So, hey John, this stuff is actually Mahout. We should be able to do this pretty easily. And now that we've taken those matrices that John talked about, the next sort of piece of plumbing is multiplying them back together. So, sounds pretty trivial. As you big data guys know, you can spend a lot of time on doing stupid things to large amounts of data. So when I was joking last week that, we're spending a lot of time John is trying to multiply, John and I are trying to multiply 2 matrices. So yeah, that's another big component, is just taking all those component matrices that singular value decomposition gives you and putting them back together so you can get the blurred version of the original matrix, term document matrix out of Lucene. And then just a bit of plumbing. We've got a blurred term document matrix, get stuff back into the Solr in some form. Our goal was just to this is all proof of concept. We're sort of playing around with ideas to help people in our Solr consulting business. So our initial goal was just to, hey, based on some threshold of score, let's just introduce these new terms back into some blurred version of the text field that we're performing this on, just to play around with it. There's a lot of other stuff we could do. And we wanted to take advantage of Solr 4's atomic update feature. Previous versions of Solr, you've had to update, delete the whole thing and then update. When you want to do an update, you basically have to give the entire document again. So if you have a giant document that's it's pretty challenging, you know, pull the whole thing out, tweak your one thing, and send the whole thing back. Now there's a nice feature where I can just say, hey, here's your blurred field. So this is the pristine goal that we're trying to get to. And for a preview of the next part of the talk, you'll get to see, I think you'll find it pretty exciting because I think a lot of people come up here and they're going to sell you their product, but we're going to show you how the sausage is made. And some of the things how software is really developed, especially in progress, because this is all stuff that's sort of still up in the air and being worked on. So I think now would be a good time to take a break and
Do that now.
okay, come see John if you have any theory questions. It's John and I. And we can swamp him with those kind of questions before we get into the sausage factory part of the day. So,
When does the break get back?
So it's about 15 minutes, so
Cool.
we'll start at 45.
cool.
I always learn about but I actually work on it.